Hello and welcome to my virtual presentation on analysis of common mode electromagnetic interference in permanent magnet synchronous machine with a fractional slot concentrated winding. My name is Addisu Tashala. I am from Ethiopia. The author of this research are me, Mr. Sao, Dr. Getachew Birru, and Professor Roberto Leidhold. The outline of my presentation includes introduction, methodology, result, and conclusion. Now let's start with introduction. It is well known that conducted common mode electromagnetic interference is one of the major problems of the modern variable speed drive. The presence of common mode electromagnetic interference in electric drives can degrade the performance of the electric drive system, even leading to the premature damage of the machine. Now, studies indicate that of the common causes of industrial motor failures, more than 50% of the electric motor failures are because of bearing damage. The primary electrical causes of the bearing failures are the common mode electromagnetic interference generated as a result of 1. Fast changing of the voltage over time, most commonly called the high dV by dt characteristics of the power electronic converters, and the other is the parasitic capacitance present in between the stator and rotor and winding of the electric drives. Of course, there are other mechanical and thermal causes which may cause bearing to be failed. So far, several mitigation strategies were being proposed by various authors to mitigate EMC problems in electric drives. However, none of the proposed solution is effective in fully evading the electromagnetic interference in adjustable speed drive. Most commonly, these mitigation strategies are classified into two major approaches. The first is the mitigation approach applied at the source of the noise by modifying the inverter, and the other is the mitigation strategies applied at the victim element by modifying the motor. Since the subject matter of this research is to mitigate the common mode electromagnetic interference at the victim element, now let us see some of the mitigation strategies proposed at the victim component. Some of the mitigation strategies proposed at the victim component are by using the shaft grounding method, by using the insulated bearing method, electromagnetic shielding method, by using the rotating capacitor method, and by using the geometrical modification method. Now, from this, except the geometrical modification method, most of the strategies proposed require an additional component which may increase the size, weight, and cost of the system, even the power loss. From the analytical equation of common mode current, as you can see from the analytical equation, common mode current depends on the two parameters. These are the amount of equivalent parasitic capacitance and the rate of change of voltage with respect to time. Now, from this we can observe that the common mode current highly depends on the presence of amount of magnitude of parasitic capacitance. As far as parasitic capacitance is concerned, most literature depicted that there are about 5 parasitic capacitance present in electric drives. Besides the other parameter, the magnitude of the parasitic capacitance in electric drives mostly depends on the number of slots. As you can see from this equation, it depends on the number of slots. Thus, the parasitic capacitance mostly they depend on the number of slots. Thus, electric machines with less number of slots will have less amount of parasitic capacitance. Therefore, in this research, a parasitic capacitance of permanent magnet synchronous machine wound in fractional slot concentric winding is compared with the conventional slot distributed winding. As you can see from the figures, there is no any structural and rating difference between the two machines except the number of slots, the volume of the groove, and the winding design. As you can see here, the distributed winding has got a high number of slots than that of the fractional slot concentrated winding, whereas the fractional slot concentrated winding have a deeper volume of groove than that of the distributed winding. Now, theoretically, since the fractional slot concentrated winding have less number of slots than that of the conventional slot distributed winding, therefore fractional slot concentrated winding will most likely have a smaller parasitic capacitance than that of the distributed winding. Now coming to the methodology, since we do not have two the same sized motor wound in distributed winding and fractional slot concentrated winding in our laboratory, so we have used the following methodology. Firstly, we have tried to model a two-dimensional model of an available 5.5 kilowatt induction machine, which is wound in distributed winding, of course, and we have carried out the finite element analysis simulation of this machine on COMSOL multiphysics software, and then we have validated the simulation result experimentally through impedance analyzer. As you can see here, this is a experimental setup. In this experimental setup, we have tried to measure the common mode impedance of this induction machine, and we have compared the simulation result and the measured one, and then we have obtained a very good match of common mode impedance between the measured and simulation result. As you can see here, almost matched to each other for a very significant amount of frequency, except some deviation at some frequencies. This is actually due to the not knowing the exact value of the permittivity of the insulation materials. And secondly, we have used the same methodology, and we have used another 60 kilowatt permanent magnet synchronous machine designed for traction of electric vehicle. We have modeled this machine on COMSOL multiphysics both in distributed winding as well in fractional slot concentrated winding, and we have tried to compare the common mode impedance, the parasitic capacitance of the machine in both windings. And finally, we have obtained a reduced parasitic capacitance and an increased common mode impedance has been obtained by employing the fractional slot concentrated winding when you compare with the distributed winding. As you can see from the simulation result, the parasitic capacitance of the fractional slot concentric winding is less than that of the distributed winding, and the common mode impedance of the fractional slot concentrated winding is higher than that of the distributed winding. This is actually helps to impede the high frequency signal. So coming to the conclusion, from the finite element analysis simulation in the result, we have obtained that a decrease of parasitic capacitance has been obtained by employing the fractional slot concentric winding when you compare with that of the distributed winding. So on top of the so far investigated advantages of the fractional slot concentrated winding, such as high power density, higher efficiency, short in turn, and high slot fill factor, additionally, less parasitic capacitance and less vulnerable to electromagnetic interference is another additional advantage of fractional slot concentric winding over distributed winding in this research. However, still further work is required to draw a generalized conclusion in this regard, because what we did is we only try to measure, simulate and compare the parasitic capacitance of the two windings, not the actual electromagnetic interference. So to draw a generalized conclusion, we need to measure or actually compute the electromagnetic interference directly. So these are some of the references we have used, and thank you so much for your kind attention, and that's all what I want to share with you today, and thank you very much indeed.